Is there further ado, or should we begin? Okay. Hello. It's nice to see you all still here. I'm astonished and delighted. And I'm also delighted to be here because, I retired a while ago, and I was never a student in Martin's lab, and I came at an older age and a later stage to his world. And I, do have a couple observations to offer about that. One being that one thing I learned about him is when he wants to test you out, he just gives you something to do and sends you off. And we heard from some of your former students about that too. It's like Martin just says, here, go try to do that, which is challenging, but also very freeing because you don't have anybody looking over your shoulder all the time. Are you doing this the right way? Trying to control it, but we'll help you, but just waiting to see what you do. And I think that's one of the reasons that the work spreads out so much. Everyone goes as far as they can and then comes back to the group. And, I see that kind of energy embodied in this group too. The other thing is, as again also reflected here, is there's a great balance between grit and expertise and a little bit of argument and collaboration, right? The experts are going to have their due. They want to make sure this is done right. They don't want skipping any steps or anything like that. But then they're open to working with people who are trying to move things forward and consolidate and synthesize, etc. And we heard a little more of that tone yesterday about how, well, is that the right way? Is this the right way? And today we see the results of spanning that into a group that can move forward in, to my mind, and I haven't been to one of these meetings for a couple of years, maybe 3 years, just incredibly spectacularly creative ways. So, I commend you all. I honor Dr. Smith for all of that. But I also challenge you to think about what's maintaining this. What has come into this that makes this happen this way, and what can you do to move that forward and continue the practices and way of organizing and thinking that have led, I think, to this really spectacularly creative project. So I guess my personal comment. I know I don't have time to say that, but I did it anyway. So, what the heck? Nobody else is following the time rules. Why should I suddenly start doing it? Okay, so my second task here is it's not exactly future applications. I'm not going to talk about that. We talked about that a lot. I'm going to talk about why is this so important and what other realms can be either, you could say, conquered or informed. You can look at it either way by this work, because I think this work is some of the most important things anybody's doing. And I'm out there working on chemicals on the outside, in the advocacy community and the people who, well, I don't think I have time to go into all the complexity of that, but that's where I am right now. So I'm seeing it from that point of view. And I want to see tools that are trustable, technically correct, usable, and done within a relevant time period. That's what I want to see. And we need you for that. So if I say nothing else, that's my main point. I'm going to show you a couple of slides, though, that you haven't seen, I think. See if I can figure out how to. Okay, number one, we need public understanding. We need public understanding of this work because just as a matter of basic political science, there's always pressure from vested interests to get what they want and reduce what they have to do, right? That might sound political. It's not political. That's a scientific conclusion that you can read in thousands of political science books. And so in a contested area like chemicals policy, people need to be able to understand what you're doing. And we can't go off into mishmash and letters and codes that no one can understand. And believe me, there are whole meetings I can walk into, not understand one word of what they're talking about. And I have a PhD and I worked in this field for, I won't say how many years. So I just commend this to remember this is an important part of the solution, is making sure you're not incomprehensible and irrelevant to the people who are the ones who are out there working for communities and talking to their legislators and caring about the public interest. So this is part of what is essential to this. Understanding and benefit is essential to public support. Now, the reason I bring this up is these key characteristics are a critical point of communications connection between the complicated assays and tests and everything else and actual humans. Because people know, for example, what cancer is. Everyone knows what that is. And they can understand some of these related terms if you spend a little bit of time with them. And the circles are really good because it's less intimidating than a long list. But a slide like this you could take to people who are worried about chemicals and wanted to understand what you're doing and explain it well enough that they would get something out of it and be able to use it. And that's why this is so important. Like I said, if you go to lots of other meetings, you don't see anything you can hang your hat on or explain. And I'm using this, this is one slide that comes out of technical work that's for a technical audience. And I'm showing it in that context that if you look at something like this, which is technical, it's a great slide, it's a great paper. There's nothing you can use here to explain to the public because it's too embedded in the analyses. So we've got to keep working on this to tie other things too, to have a point of connection. Second is my second point. Civil society is active on SAHAR products and practices. I would argue more than there's any regulation right now. You know, who's regulating anything right now? I mean, there's a little bit, but there's not really that much. And there's a huge amount of effort going into this. And it's all being done by amateurs who don't have any of your information. And we've got to, I would argue we need to change that. We need to make this transparent to other people who don't need to go to prove that something's a known carcinogen. They can say, oh, it causes this, this, and this. Let's not use that. And then there's this issue of keeping up pace, what to do about all the chemicals. I also, Kate, I think you had this in your this diagram in your slide too. It's, and this is really left over from my previous slide, but I'm going to come back to it. We need to think beyond review. You know, we need to build data streams, structures that are prospective, that feed the information that we need directly to structures we can draw on. I know there are people interested in that, and we've got to get there. But this can draw on the cases too. We need to create transparency across these different spheres of review and move the rate of examination. Again, I'm not going to say review because I want to be prospective, to something more like hundreds or thousands per year, not two a year. And Martin mocked me when I said, well, there's hundreds of thousands of chemicals, et cetera. Appropriately so, because I know we can't deal with that. But there are people and initiatives trying to look at that big picture and how to organize it. And this work is key to that because it creates a way of organizing that can cross some of these different fields. Organizing data, drawing together evidence, bringing together information with expert and trusted reviewers. That's the crux of all that, and that's what we need. So I'm going to end with that, and thank you all for very wonderful discussions, and ask for additional comments from my esteemed colleagues who are going to talk about. I'm not sure who's the middle child here, but I will let the appropriate child go first. Hello? Kathy's going to talk about issues related to computational methods.
Yeah, I didn't realize quite how many teams Martin had. I'll try not to be jealous. So thanks to Martin for, I think we're pushing 5 years now of great collaboration doing computational toxicology, Martin and Michelle and a larger team. And it's been a lot of fun bringing, we brought some really interesting questions to us and allowed us to play around and develop new methods. And I guess now that you'll be out of a job, you'll have more time to work. This is great. Computational approaches to toxicology, it's a little hard to sum up, but the main takeaway I'd like you to have is optimism. There's been incremental approaches, incremental improvements in computational approaches year on, and as years turn into decades, increments turn into real progress. And computational models that people like Kamal and David are building today are just miles ahead of where we were 10 years ago, and we have every reason to expect that will continue. And computational models are operating at a variety of levels. Some of the approaches we saw earlier today were essentially big data approaches that are really interwoven with experimental methods, where we take some sort of biological pathway tied to an individual KC, maybe a sub-pathway within a KC, or perhaps transcending KCs, but nonetheless, an individual pathway and individual chemicals, building some sort of mathematical model that ties the reactivity in that pathway with the structure of the individual chemical. And let's say you experimentalists have done hard work and generated a data set of 1,000 such chemicals. We computational chemists can help you leverage that and take that where we can now help you predict taking your 1,000 inputs, predict toxicity on tens of thousands, hundreds of thousands, millions. And it's a great partnership, and we should be really, really optimistic about that. One of the things that I have really been enjoying in recent years working with Martin is at the other end of the spectrum, which is, as a chemist, working with atoms, at the actual molecular level, doing atomistic modeling of small molecules interacting with individual biomolecular systems. And each of our KCs, you can think of those as, at the very least, at the initiating step of that biological outcome is some exogenous chemical interacting with a biomolecule. And once again, you should really be optimistic about our ability to model at that level. There's really been just tons of developments. Some of them are just brute force, old algorithms that have now become useful just because the hardware is there that we can do them at a useful scale. So you'll see in the literature in coming years a terminology of free energy perturbation, which is becoming a method for giving highly accurate ranking of ligand binding to biomolecules. And the algorithm has been around for decades, but we can finally do it at scale. Also, a lot of the familiar methods of molecular docking, molecular dynamics, those are going to become more accurate with the rollout of polarizable force fields. Just basically, that's right, yes. My one technical term. We're just going to be able to model non-bonded interactions much more accurately. And, you know, when a couple of proteins get together to form a larger structure, or a small molecule interacts with a biomolecule, that's led by non-bonded interactions. And we'll be able to model that much more accurately. So be on the lookout. Polarizable force fields.
Wait a minute, it was already covered in Star Trek? Just like those things that you put in your ear and walkie-talkie? Exactly, okay. All right, so thank you for those great introductory remarks and for the whole day. And I too used to work at EPA before I had the opportunity to come back to California. I was also in the School of Public Health here at UC Berkeley, and it was really an amazing place to learn. And California has been a real leader in thinking about science and environmental policy. And I like to think about this as, I think Amy did an excellent job of talking about kind of what is our, kind of where are we trying to go with all the things that we're talking about, and thinking about, well, where's our end goal when we're thinking about this important component towards getting there, which is addressing these, it's 350,000, by the way, chemicals registered on the marketplace globally, and these health problems that we know people are suffering: cancer, neurodevelopment, asthma, etc. And so now the KCs offer this opportunity to move more quickly from the science to taking actions to do better to identify these and move them into a policy arena. So I wanted to get down to the specifics thought I had, because one of the things in this session is how do we like provides more specific advice as we're moving forward, because now we have all the structure and the scaffolding to take actions more quickly, right? Cancer has really been at the forefront. Now we can move down the other health endpoints and think about them in moving that. But I think it's like we have this, I think the other thing that was a really important point is to think about this as a continuum of evidence, right? We have possible, probable, and known. And I think that that offers us an opportunity, like California started to use these KCs in Prop 65, and everything is based on a known, right? You have to be known carcinogen, known reproductive developmental toxin. But what about the other opportunities that California has on the policy landscape? Because California has many environmental policies, as well as the things that they do have national and international resonance. So can we think more strategically about looking at the ways that we can use KCs to identify possible hazards and move those into policy opportunities, maybe not through Prop 65, but through, like you're saying, drinking water, hazardous air pollutants, and pesticides. I think that getting down to identifying those priorities, not only the chemicals that we have to do, but the opportunities to identify these possible reproductive, neurodevelopmental, immunotoxicology, kidney toxicants, and then looking at how we can act on those, I think is a practical next step for how we can realize the value of the KCs in addition to cancer. So that would be my thought after listening to many, many pieces of information and thinking about how we've created this amazing scaffolding to allow us to use more upstream information in doing the work that we need to do to protect health. So.
Okay, well, thank you all. We don't have time for a debate now. And does anyone have anything else they'd like to raise before we adjourn this panel and turn it on to our other fearless leader, Dr. Zeiss? Okay, well, we thank you for your attention and